Hello there, this is Tyler Jones. Today we're going to be looking at mass spec, IR, proton NMR, as well as carbon NMR for C14H12O2. Without further ado, let's get started. Okay, so first of all, we are going to start off with mass spec. Let me go ahead and write that in here. For C14H12O2. So to begin with mass spec, the first thing we're going to locate is our M+ peak, which is our farthest rightmost peak, which gives us our molar mass. As you can see here, 212 is going to be our M+. And if we do the math, adding up the molar masses for 14 carbons, 12 hydrogens, and 2 oxygens, we do come up with 212, so that is fantastic. The next thing we're going to take a look at is our base peak, which is our tallest peak, which obviously we can see that here at 105. Now, if we go ahead and take a look at the difference between our M+ and base peak, as well as our several peaks that are labeled in between these in reference to our base peak, if we take the base peak subtracted from each of these numbers, we typically can find some sort of hint for a structure that will be within our total structure. I went ahead and did the math referencing the compound chem worksheets and was not able to find any hint or any structure to come up with those differences. So in this instance, they were more or less useless, but in some, they can be extremely helpful. The last major peak or piece that we're going to take a look at here is our degrees of unsaturation. This is most definitely the most important part of mass spec, as it gives us our number of pi bonds and or ring structures. So to do that, use the formula 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of hydrogens minus the number of halogens all over 2. And if we do that math, we get a number of 9. So that means we can either have a combination of 9 pi bonds and or ring structures within our structure that we're going to come up with. So now that that has been completed, we are going to move on to IR, which is going to help us determine functional groups within our structure. As you can see, I've already gone ahead and marked off the zones and labeled their respective numbered locations. I've also marked out the zones that we will not be looking at. I'm going to go ahead and label specifically zones 1 through 5 as well as the fingerprint region. Okay, now that that's been completed, we're going to go through each zone referencing the compound chem worksheet for IR to determine if our peaks show any sort of functional group. So definitely we have this large peak here in zone 1. It also has a tongue-like look to it, which definitely hints towards an alcohol going to be present within our structure. Zones 2 and 3 both do not really have any peaks, even though these have numbers on them here in zone 2. They're really not of any significance. So for zone 2 and 3, we're going to label it as nothing. In zone 4, on the other hand, we have a very, very strong peak at 1677, and in this zone that represents a carbonyl, and in zone 5 we also have a slight peak. It is not numbered, but we can still see it coming down right about here, and that's going to hint towards an aromatic. Typically one doesn't need to read into the fingerprint region, but since we have such strong peaks here at 1261 and 1201, I went ahead and looked into that, and that also points to the presence of an alcohol. So now that we have completed mass spec as well as IR, we are going to move on to proton NMR. Now that we've been through mass spec as well as IR, we're going to jump right into arguably the most important part of this whole process, that being proton NMR. So I have come up with a structure that I believe could fit this, and so I'm going to go ahead and draw that in for you now. Okay, now that the structure's been drawn in, and you can see that there are the correct number of carbons, hydrogens, as well as oxygens, we're going to dive right into trying to explain this in relation to the graph that we're given here. So the first thing that I actually want to do is label the peaks as whether they are a singlet, doublet, triplet, etc. And so I'm going to go ahead and do that for you now. Both of these sections can be expanded. As you can see on the bottom, this is this expanded, and bringing this expansion is this top sheet right here. So as you can see with that, I'm going to label this as a doublet, this as a singlet. Our 5H here is going to be a triplet. Our middle 2H is also going to be a triplet. Our 1H here will also be a triplet. And finally, our furthest most left 2H will be a doublet. Okay, now that that's been completed, we are going to move on due to the sheer size of this structure. I just went ahead and circled all of our hydrogens or protons, and I labeled them respectively to their d-shielding, and I'm going to go ahead and explain that now for you. The first thing I want to look at and point out is wherever it says these, such as 2H, 1H, 2H, 5H, etc., those are our integration numbers, and if you add all those together, they should add up to 12 to match our number of hydrogens in our formula, and they do correctly, so that's perfect. And now to begin going through the de-shielding, the furthest right or upfield is the least de-shielded, and the furthest left or the most downfield is the most de-shielded. So our number one here, I have circled our alcohol or our proton attached to the oxygen to form the alcohol. This is labeled as the least deshielded simply because this exchanges makes it extremely unstable. It's constantly coming in and out, connecting and disconnecting, so it isn't read very well. That is going to be where it says exchanges here, and it's labeled correct or appropriately. Moving more downfield, I have circled this hydrogen, which is attached to this central carbon here. I have done this as this would make sense if this structure had some sort of impurity in it. This would be the reading as to where this hydrogen would be, and it makes sense as well because this is an aromatic region, which matches up with this integration of 5H that I've labeled here. That this aromatic has to be in this aromatic region, as well as the hydrogens in this aromatic are also in the aromatic region, but they're separated appropriately due to their closeness to this double bonded oxygen, which is extremely electronegative. So due to these two aromatics and this hydrogen being in the center of them, even though it is close to this double bonded oxygen in theory, this is where it must end up. To explain this further as to why all of these hydrogens are labeled here, again, this is an aromatic region and this is an aromatic structure. The integration here is 5H, and that's why there's 5 hydrogens or protons, and they are less deshielded than this aromatic region due to this alcohol is very inconsistent as to when it is attached, whereas this double bonded oxygen is always there and is always pushing the hydrogens in this aromatic region farther downfield. So that is why these are here. At this integration of 2H, the number 4 has been labeled with these protons here because they are less deshielded than these two for number 6, as well as this one for number 5, due to the 3D structure would put it closer to this double bonded oxygen. Moving more downfield, or the more deshielded, at this integration of 1 hydrogen would be this outside hydrogen labeled as number 5 here. Again, that is due to its symmetry and proximity to this double bonded O, and potentially even where this OH is coming in. And finally, our most deshielded hydrogens would be these two labeled as number 6 here, because they are in direct proximity to this double bonded oxygen. Now finally, for this proton NMR, I have went in and labeled our N+1 rule for all of our groups, which determines it shows us the proximity of protons. As you can see for these, looking at the adjacent carbons, taking this one in reference, each adjacent carbon has 1 proton, so our N+1 would make it 2 + 1 = 3, and that would be the same for all of these. And that same rule applies for the rest. And if we look through, as well as how the peaks are labeled and our integration, they match up well for where our deshielding of the proton or the proton groups have been labeled. Now that proton NMR has been tackled, we're going to move on to the final step of carbon NMR. Alright, now we're going to begin our final step here, looking at carbon NMR. So I just wanted to quickly show you our location here down at the bottom. This is our graph for carbon NMR. Again, as you can see, like in our proton NMR, there are 3 groups here that could be expanded to show us a little bit more information, and I'm going to go ahead and show those to you now. Start moving from right to left, our first expansion here. You can see on the top of this image, in the middle, here's our expansion for that. And finally, our leftmost expansion here is the image for that. So as I work through on the main image, if you need to reference these through my speaking, you can go back and do so. Okay, again, due to the large nature of this structure, I've gone ahead and redrawn the same structure that was drawn in on HNMR, and I have went ahead and labeled the carbons this time instead of the protons in order of deshielding. The deshielding in CNMR works the same. Left is downfield, the most deshielded, and right is upfield, the least deshielded. So I'm going to go through and walk you through as to why I did what I did. So first, starting at the least deshielded position, I chose the carbon that is attached to the alcohol group. Again, this is done because the alcohol group exchanges, as well as due to symmetry in the locations of the cyclic structures here. This points to our being in this 76.1 zone. That matches up well. Moving on to number 2, our dark green here. I chose these 3 carbons to fit into this group at 127.7 due to involving the ring structures. They are the least deshielded carbons due to they are the farthest away from any oxygen. Again, considering they are extremely far away from the double bonded oxygen, which doesn't leave, and they are far away from the alcohol group, which does come in and out. So that's why I chose for them to be there. Moving on to the third least deshielded at 128.5. That is our dark blue here. I chose these 2 carbons on this ring structure. I chose those 2 considering they are in similar locations in a 3-dimensional sphere, as well as they are closer to this double bonded oxygen than, say, these 2 over here, or even these 2 carbons right here, because obviously those are closer. So I chose them to be 3. Moving on to 4, the fourth least deshielded, 128.6, just slightly more. I chose these 2 carbons right here. Again, I grouped them together because they're in similar environments, and I have them being a little bit more deshielded just because of the fact they are not on the outside of a ring structure, they are on the inside, which does put them slightly closer to an electronegative oxygen. Moving on to number 5, slightly more deshielded. At 129.1, we have 2 of those listed here. So again, I grouped these 2 carbons, the inside carbons closest to this double bonded oxygen on this ring structure, because as you can see they are quite close to that, and it would make sense as to why they would be more deshielded than these 2, for example. Moving on to number 6, our 133.4, even slightly more deshielded. I chose this outside carbon here. You may be wondering why, considering in this example it looks to be farther away than, say, these carbons. But in terms of how this would sit as a 3-dimensional structure, it would not be linear like this, and that would actually be more susceptible to be affected by an electronegative oxygen. So that is why this carbon right here is ranked as 6th and even more deshielded than the ones that have been shown before it. Number 7, slightly more deshielded at 133.9. I chose this singular carbon right here. That is because it is less deshielded than, say, this carbon or this carbon, for example, but it is more deshielded than the ones that have been shown previously because it is coming in towards these 2 oxygen groups. Moving on to number 8, this has a little bit more of a jump to be more deshielded at 138.9. This makes sense because we flip from this ring structure to this ring structure on this inside carbon, and this is much closer than this one. Number 8 is much closer than number 7 to this double bonded oxygen, making it more deshielded, pushing it more downfield. Now that we've looked at 8, we're on our last group here, number 9. At 198.8, that is a much higher group, and it does line up with what we would see as a C double bonded O, and we do have that exactly right here. This carbon being directly double bonded to an oxygen would be, of course, pushed the most downfield, and be the most deshielded. That concludes our carbon NMR as well as other processes. I hope this structure makes sense to you. And I thank you for listening. Again, this was C14H12O2.